Wherever imaginary numbers are introduced, the name imaginary tends to be described as a slur, an unfortunate legacy of how they were seen back when they were not yet properly understood. In fact, there are two other important sets of numbers with psychologically charged names, the irrationals and the negatives. It's just that in the case of negatives, we mastered the art of building intuitions so well that any business today can rely on all their customers knowing what they are and how they work. Personally, I think the name imaginary is great. The natural language meaning of the word ties important abstract realities together and enables us to quickly recognize where they show up in everyday life. But to be able to take advantage of that, we first need to rebuild that abstract tower in the natural language of intuition, staying tethered to the human world. We want to learn how to count in imaginary, and we will be able to do that once we understand how to count our way to imaginary. Let's begin by counting some oranges. If we do only one act of counting, it's the same as just saying, here's an orange. Counting once is equivalent to identifying something and leaving it unchanged. This will be important later. If we have a bigger amount to count, we'll start getting faster by being able to spot groups and adding them at once. You see 3 oranges, grab all 3 at once, add them to your pile. If you are able to spot 3 groups of 2 at once, you can pull all of them at once, and you'll have added 6 in one go. You are obviously doing addition and multiplication, and you don't have to think about the order in which you are doing this because those operations work the same in both directions. But instead of thinking about the order not being important because addition and multiplication have this property, you can instead recognize that they are both automations of counting that do not change anything about counting itself. They just empower you to do more of it at once. This has an easy to overlook consequence. The order in which you count gets erased. You can throw everything you're counting onto a pile, and the pile forgets the order. Counting numbers themselves have an order in which they appear. That's how we can figure out which are bigger and which are smaller, but they don't say anything about the arrangement of the result. You can also see this as erasing individual differences between the things being counted. Oranges are not necessarily all the same, but this isn't relevant when counting because everything just ends up in one place in no particular order. We can now share these oranges by just letting everyone take 1 or 2 until the pile is depleted, and that's fine as long as we don't care that everyone's share is equal. That would be just another example of counting. However, if we want to give people equal shares, we have a problem that doesn't necessarily have a solution. With our specific example, something interesting happens. Thinking in terms of integers, we cannot divide 9 oranges between 2 people fairly, but in this real-life situation we can, because we can roughly balance out the weight using one of the smaller oranges. Likewise, we can abstractly divide 9 by 3, no problem, but in our case, one person will be less happy because they got 2 small oranges, while others got 2 big ones. For division to work as expected, the things we are dividing must be uniform. So let's take 1 orange, make it a bit more abstract to erase the individual differences, and then make 9 perfect copies out of it. If we now divide it into, say, 5 equal pieces, we can see that this isn't quite enough. Individual pieces are not quite the same. We need to make it even more uniform. So we'll turn the oranges into orange juice. Cool, we can divide this into any number of pieces we want, and the pieces will always be the same. Nobody can complain. This changes the meaning of the number 1 though, because we've completely lost track of a single orange, and juice is not something countable. But the compartments we divided our juice into are. What happened was that we turned the idea of 1 upside down. First, it was an element we could use to build a whole, and now we start with a whole and break it into pieces that can be counted. This is important for our story because by upgrading the number 1, we have also upgraded counting. It becomes more visible if we package all the juice into a carton. Now we have a thing that exists in real life that we can count in a traditional sense, and inside it we have a substance we cannot count but can divide into as many equal smaller units as we want. These smaller units have exactly the same properties as the whole, while a carton stops being a carton when you break it up. We went from having only 1 counting unit for everything, the number 1, to now having as many different units as we can think of ways to divide a whole. If this whole container of juice is 1, then these individual compartments are 1/5, one of our new units. You can still count those using natural numbers. It doesn't matter into how many pieces you divide something evenly, it's always just some countable number and nothing is left over. Now let's merge the two meanings of 1 into a single concept. To illustrate this, I'll be using wheels of cheese. We can count them, but not the stuff they are made of. That is an uncountable substance, just like juice. In contrast to juice though, they don't need a container to hold them in place. A wheel of cheese contains itself. So they are perfect to keep track of both natures of 1. Let's say you have 3 of them and you are dividing between 4 people. You can always cut every wheel into the same number of pieces as you have people, so 4 here, and then give each person 3 of those quarters. The fraction just gives you an immediate answer to your question because it just is the question, unchanged. The numerator is how many wheels of cheese you have, and the denominator is the number of people. Fractional units, halves, quarters, fifths, and so on, turn division back into counting. When dividing cheese, there is clearly a difference between a cut and the thing that exists between 2 cuts. An idealized cut splits the cheese perfectly, meaning you can cut your wheel into as many equal slices as you want. There will always be cheese in those slices. And if you add up all the slices, you get the whole wheel back. The cuts themselves didn't take any cheese out of the wheel. So we could count the slices, or we could count the cuts. Both works. On a wheel, we derive at the same number. Therefore, we can label with counting numbers like this, or like this. This suggests there are some numbers that aren't made of fractional units hiding in the cheese, and paradoxically, together they make up all the cheese, since the fractional units left all the good stuff intact. What's also hiding in the cheese are the concepts we need to reach out to imaginary numbers. We have gone from counting discrete real-life things to labeling regularly spaced boundaries within a thing. This gives us the power to use numbers not just as an amount, but also as a measure, because we can now rely on their arrangement being uniform in space. If we now take the entire rim of the wheel to be a measure of 1, we can see yet another nature of this number. It is an uninterrupted continuum, and there are always places on it you cannot define by splitting it evenly into pieces. In fact, there are no ways to systematically account for all the places where you could make a cut in a length of 1. This fact has been rigorously proven in many different ways. But there is a kind of a cheat we can use to define them anyway. We just say it's all the places on a continuous line segment and call it a day. Applying that idea to an infinite line gives us the real numbers. We just start from the assumption that real numbers extend continuously without any gaps and call every location on that line a real number. Then we say that fractions are rational real numbers, and everything we couldn't find by listing the fractions we call irrational. The fact that this is a negative definition makes them a bit elusive. Everything but is a very open statement. New kinds of numbers are still being found within the irrationals even in this century. We can't properly identify all the kinds that could exist, and we can't properly categorize some numbers into rationals or irrationals. It's a bit messy. The reason to go into them in the first place is that they hold the key to continuity. The cheese between the cuts is necessary to get where we want to go. We don't really need to understand every number that makes the continuum, but we do need to look into an example that is irrational to see how such a thing arises in the first place. The operations we've done so far cannot produce any of them, so we need to look further. We're going to start by counting something arranged. Tiles on a chessboard. We know it's enough to just count the tiles along one side if we want to count them all, because multiplying that number with itself will let us skip right to the finish line. This serves as a simple squaring calculator for numbers between 1 and 8. The number of tiles stacked into a square shape above some number here will be the square of that number, and vice versa, we can read square roots of square numbers by just reading what number appears at the edge below them. We're going to consider two kinds of chess pieces, a rook and a bishop. In one move, the rook can travel as far as it wants into one of the cardinal directions. so it can reach any tile on the board from any other in at most 2 moves. A bishop moves diagonally as far as it wants in 1 move, but it's stuck with the color of the tile it started on. But among the black tiles, it can reach any of them from any other in at most 2 moves, just like the rook. It's kind of like odd and even numbers. If you skip ahead by 2 instead of by 1, you will stay stuck with either even or odd numbers depending on which kind of number you started on. The rook would also be stuck on a color if it was forced to move 2 tiles at a time, even if it could choose between 2 in a row or doing a turn between them. Although the bishop makes this double step faster, it travels a shorter distance by cutting across. This shorter distance is a square root of 2 via Pythagoras, we all learned that, and we know practically that cutting across saves a bit of time. A very funky amount that's not trivial to calculate by hand. Let's think about this a bit. We are in a countable space of tiles. How do we get to a number we can't count to using tiles? To answer that, let's try to put the bishop into a space of countable tiles corresponding to its freedom of movement. We'll just put it down in this corner and populate the diagonal of the board with adjacent tiles that match the units it travels between. This is the countable space along the diagonal from the bishop's perspective. These are obviously bigger tiles than the tiles of the board, and the unit of bishop's travel now matches the side length of one of these squares. If we inspect one of these bigger tiles superimposed on a board tile, we can count up these small pieces that are each a quarter of the size of a whiteboard tile and add them to the whole blackboard tile in the middle to get 2 board tiles. We need 2 regular board tiles to assemble 1 bishop's tile. Marking all the places the bishop can reach on the board, we can see there are half as many of them, but being half the size, they add up to exactly the same area as the chessboard itself. This explains how the bishop is constrained to tiles of 1 color, but it doesn't help us figure out the distance it travels, since we can't arrange these tiles together into a square shape and read the root of that square. Let's see what happens if we try to work out the square root of 2 using the chessboard as a calculator. To do that, we need to align one of the bishop's tiles with the corner of the chessboard where the bishop sits. Okay, that is very awkward to read. The ideas of counting and measuring are clashing. To do measurement, we need to shift numbers so they aligned with edges of tiles, the cuts between them, and we need to add a 0. The measuring numbers we get this way have an origin and a direction, unlike counting numbers, and they grow into a direction continuously instead of popping up in an order. This happens with squares too. They also grow continuously from an origin into a direction when we use them for measuring. Only in this dimension, they grow faster because the actual shape grows in 2 directions at once. The consequence of this is that we are dropping shadows onto our regular number line faster than counting numbers appear on it, and therefore we can only find answers for specific square roots. By asking what the square root of 2 is, we are pulling a number out of the continuum that isn't reachable through some analog of counting. But we could think that we could find an answer by just making sufficiently small fractional units. It turns out we can't though. Why is that? We want 2 things: to show that the square root of 2 cannot be a fraction, and the reason why that is that extends to all natural numbers that are not perfect squares. Because it's generally true that if you can't find the square root of an integer among integers, you don't have to check fractions. It's not going to be a fraction, ever. To do this, we only need to show that fractions that are not already integers don't square into integers, because if they don't, they will never be answers to square roots of integers. What makes a fraction not an integer? The fact that this number up here is not a multiple of this number down here. Let's take an example. 5/4. We're gonna be marking everything we know not to be an integer in red, and everything known to be an integer in green. 5/4 doesn't simplify, which means that it's only a whole number in multiples of 4. Now we look at squaring this number. 5/4 multiplied by another 5/4, which we can also see as multiplying by 5 first, and then dividing by 4. We know already that multiplying by 5 gives us another non-integer fraction because 5 is not a multiple of 4. It can't be, because if it was, 5 quarters would have already been an integer itself. So this holds generally. Now we have a fraction that we know is not an integer, and we are dividing it by 4. Dividing a non-integer by an integer. Can that ever be an integer? If it could, it would mean that we could multiply two integers and get a fraction that is not an integer. But this is clearly not the case. We see that if a fraction is already as simplified or reduced as it can be, and it's not already an integer, squaring it will definitely not produce an integer result. So any fraction that doesn't reduce to an integer also doesn't square into an integer. From this we know that any square root of an integer that doesn't have an integer answer also doesn't have a fraction as an answer. Visually, this happens because once you draw a square of countable units, all the numbers sitting at the bottom are busy answering questions about their perfect squares, and there are no spares left to address the questions about the other square numbers. If you zoom in and create fractions, the same thing occurs. They're all already taken. So how do we define where that place is? We kind of don't. We just leave the question in its original form, like we did with fractions. We say it's whatever you get when you take a square root of 2, for example, and that's it. If we wanted to work it out to some precision, we're doomed to guess and check forever. Any approximation we make will have to be a rational number, because what else can it be? When you write a number in decimal notation, you are just writing a fraction expressed in units of tenths, hundreds, millions, however many places you need. There's just nothing better to do. Alright, with continuity, measures, and units together, we arrive at the concept of array of positive real numbers. An uninterrupted continuum that begins at 0 and extends to infinity in a particular direction we chose to draw the ray in. We don't normally associate numbers with a direction, but that's just because the real numbers obey the direction we choose to measure in without complaining. This obedient behavior is contained in the unit of this ray, the number 1. It becomes a bit more obvious when we consider that a different unit, such as the number -1, doesn't just follow the direction we chose. It doesn't freely choose something on its own, but it does reverse the direction that we have chosen. Our familiar alternative unit is again a consequence of an inverted operation. We got fractions by inverting multiplication, some irrationals by inverting squaring, and we get negatives by inverting addition. Negative numbers may appear mundane from our modern perspective, but they were elusive for most of history, and it is only through them that we really start to notice that numbers can have directions relative to each other. Moreover, negatives live away from all the other numbers we've defined, behind the singularity of units. What I mean by singularity of units is that you can think of 0 as having no unit, but you can also think about it as having all the units at the same time. 0 amounts of all quantities meet at a common point. It's an origin of all measurement, so it's a quantity in all units. We're accustomed to looking at real numbers as an infinite line spanning in both directions, including positives and negatives, but I think there are advantages to considering it as two different real rays pointing away from each other, where one of them is a bit more real than the other in the everyday sense of the word. If we apply the numbers we've encountered so far to something physical and tangible, like wheels of cheese, we can make sense of any quantity we can find on the positive real ray. We could have a square root of 2 of a wheel of cheese, even if precision might be an issue. We just know what it means. It's a real thing. But you can't have -2 wheels of cheese without offering some explanation of what you mean by that exactly. You'd need to say something like, oh, I actually have a cheese shop, and I have an outstanding order for 5, but only 3 on my rack. Doesn't that make those 2 wheels of cheese sort of imaginary? You can't see them. You can't give them to someone. You are imagining how many wheels you'd need to have to be able to fill the order. You could give a name to these imagined wheels. Let's say you call them missing wheels of cheese. And then you could write -2 wheels of cheese equals 2 missing wheels of cheese. You can probably already observe that this also means that minus 2 missing wheels of cheese is equal to 2 wheels of cheese. The negative unit has this property of creating a mirror world, which, in terms of that unit, looks and works exactly the same as the regular world, including the fact that it has a mirror image accessible through a negation of its unit. This is most obvious in the everyday intuition of walking. You have to choose a forward direction first, but once you've done that, backward pops into existence fully defined as well. And if you turn around, backwards becomes forwards and everything works exactly the same. So you're not going to be confused if I tell you to walk minus 2 steps forward. Maybe you'll think it's a bit weird, but you'll understand me. And I'll ask you to walk in even stranger ways later. This brings us back to squares and their roots. We know they also come in 2 varieties. Any number we choose to find the square root of, or now that we have negative, roots of, gives us 2 answers, one being the negative of the other. Earlier I just quickly glossed over how square shapes grow in 2 directions at once. Now we take a deeper dive into what this means. We had to get ready first by focusing on the relative nature of directions. They are not like north and south that point somewhere specifically in the real world. They are more like walking directions, freely chosen, but with specific relationships to each other. With 2 directions that can form squares, this gets interesting. We start with one direction that we can completely freely choose. Conventionally, at least in the West, we pick right. Then we choose another one, a bit less freely, because it has to be orthogonal to the first one. So it could be up or down, but again conventionally we choose up. This sneakily establishes a turn to the left as positive. It's a direction in which we choose a fresh degree of freedom we want to expand into. Normally, when we think about directions, left and right don't have a hierarchy like forward and backward. Neither comes first. But once we make this choice, the hierarchy gets established. Left now comes first. It's a forward in a new direction. Now that we're focused on these nuances, we can look at forming squares a bit more carefully. We will extend our 2 chosen positive directions, which then force the choices of the 2 negative directions, and we will draw them from the center of a chessboard to have a visual reference for units. We shouldn't forget that the orange ray pointing to the right represents our primary choice that everything else is relative to. These are actual real positive numbers. Negative reals span opposite of them. Now let's think of measuring in terms of painting with a color corresponding to our rays. If we paint in a positive direction, we'll be using orange paint. If we do it in a negative direction, blue paint. We won't be using red and dark blue for now because they don't represent real numbers. They are just directions we've established relative to real numbers. The brush we're using to paint is a bit magic though. It paints with the color you dipped it into when you pull it in a positive direction, but when you pull it in a negative direction, it changes color. This reflects the behavior of negation. With that in mind, let's now look at squaring the number 2 in terms of multiplication. We first measure out a length of 2 on our orange ray, so we dip the brush in orange, and then we paint for a stretch of 2 in another direction to the left of it. That direction is positive because of the choice we made when we drew the axis. A turn to the left creates another degree of freedom identical to the one we started from. Now let's square minus 2. We first measure out 2 in the negative direction, so we dip the brush in blue paint, and then we paint with that brush in another negative direction, so the brush changes color to orange again. We've done the squaring in 2 steps, like multiplication, but if we look at squaring as an invertible operation, which we need to do to consider square roots, it actually works like this. It takes a unit square and stretches it into 2 degrees of freedom simultaneously. We can now ask what would happen if we painted a square by going against the chosen direction when choosing a new degree of freedom. For example, starting from the positive reals and expanding to the right. This would make our brush switch color because now the degree of freedom has a direction opposite from the one we started in. So a square in this corner would be blue. Let's paint it in. Something similar will also happen in the upper left corner too. This time, the brush would be blue, and it would not change since the opposite of a negative direction is positive, and positive doesn't change color. Let's paint that in too. What we have here are positive and negative squares. We could have of course also done this by just considering what the numbers on the axes multiply into, but I wanted to make sure we think about directions in relative terms. Now we're going to take advantage of that to find roots of negative numbers. We always created a new degree of freedom by opening it to the left. When we invert that, we are collapsing the space we've created into the direction on the right. So for our orange positive squares, it's clear. The upper right one collapses into the positive reals, and the lower left one collapses into the negative reals. What about the negative squares? If we take the blue square in the upper left, collapsing that one to the right would bring us onto the red ray, and the one down right to the dark blue ray. The red and dark blue numbers we have just found are what's called imaginary numbers, and the whole axis on which they sit is called the imaginary axis. We have found them thanks to keeping track of how we opened new directions to do squaring in. And now we see where imaginary numbers live relative to the reals. They are just a turn away, similar to the negatives. All that's missing is to label the axis properly by giving it the unit these numbers are expressed in. We use the letter I for imaginary and state that everything on this axis is a multiple of that unit. So what is this I? Generally speaking, it's a unit that sets the direction of measurement halfway to backwards. We can write this algebraically as multiplying by -1 half a time. -1 raised to the 1/2 power. This is kind of the same as the square root of -1, with a slight annoyance being that it's not really clear if you mean both -I and I, or just a positive I. Visually, both these units come from collapsing negative unit squares. Imaginary numbers turn out to be nothing more than numbers spanning along different directions, which is not so dramatically different from the negatives. To use them properly, we just have to remember that they don't care which way is left and which is right. We set that preference for them by picking which way of turning we consider to be forward. We are now ready to do some counting with imaginary numbers. First, we'll do walking, as that is the closest to the abstraction we've just learned, and then we'll move on to an example that gives credit to the name these numbers have been given. To count steps in imaginary units, you can probably guess, we'll just pick left as our forward turning direction, and that will give us the option to express any movement on a flat surface. Earlier, I asked you to walk -2 steps forward, like this, and now I will ask you to walk 2i steps forward, keeping in mind that we agreed for left to be a positive turning direction. So you just go sideways 2 steps to your left. This way I can give you full-on instructions on how to get somewhere in a city grid by just chaining them one after another. You could also add all the real parts and all the imaginary parts together, and you'll get a number that you could read as a right-angled triangle that describes a straight line path to your destination, if you can fly over obstacles. That is called a complex number, a mix of real and imaginary, and it's basically a number that can communicate both a measure of distance and a direction relative to forward. You can now communicate not just right-angled turns with numbers, but any kind of turn. So instead of this awkward sideways walk, you could also read them as first turn, then walk. This is possible because complex numbers also have units, just like fractions or negatives do. To understand this, we need to take a step back. No, I mean metaphorically. We've created fractional units by inverting multiplication and applying it to the number 1. Since multiplication adds equal lots together, division had to produce equal fractions that add up to a whole. This is what gave us uniformity of measure. When we take a root of the number 1, we get every relative direction that, when applied that number of times, ends up not changing the direction at all. For square roots, that is just the opposite of 1 and 1 itself, And for fourth roots, we also include I and minus I, because you can take 4 left or 4 right turns and end up facing forward again. You'll notice that minus 1 works because we just turn around twice, and 1 works because we don't turn around at all. This works for any degree of root. We can partition the circle into equally spaced directions, just like we could cut the cheese into equally sized slices. If we split it into 5 directions, each of them will be some number of fifths of the way around the circle. And going around by that much 5 times will just turn us around the circle fully 0 or more times. These are called roots of unity, complex numbers that contain pure direction, like minus 1 or I. When you multiply by them, they will just turn you around by some angle, but won't affect the distance you are traveling. So what do those look like? One example would be the movement of the bishop. It travels along a diagonal direction for the length of a square root of 2. Its actual unit of movement is 1 plus I, but that unit is square root of 2 long as a diagonal of a unit square, so it's not a root of unity. To get a root of unity for that direction, we'd need to divide out the magnitude, the square root of 2. And by doing so, we'd get a pure diagonal direction which corresponds to one of the 8th roots of 1 because it represents 1/8 of the way around the circle. For the walk we've done, we could also get a pure unit of direction by dividing out its length. Again, the length would be the long side of the right angle triangle, so we'd compute that number and divide it out. Now it's time to count some imaginary things. Remember, we used negative numbers in a similar context when we mentioned not having enough cheese to fill an order. The missing cheese was some sort of imagined quantity we used for accounting. We can expand on that by using actual imaginary numbers. This will be the unit we use, 1 imaginary wheel of cheese, that is equal to I times 1 real wheel of cheese that we have on the rack. Let's set up a simple sales cycle. We have cheese on the rack, cheese in outstanding orders, cheese that shipped away, and orders that have been cleared. We can push cheese around this cycle by multiplying by I. Shipped cheese, formerly known as missing cheese, we get by multiplying imaginary or ordered cheese with I. Then we get a cleared order by multiplying I with shipped cheese. And finally, we can handle a returned order by multiplying with I one more time. Okay, let's put those rules to the side and do some business. We'll start by setting the status of our shop to 0 here in the corner, and every time something happens, we will add to that number to update the status. We first procure 20 wheels of cheese and stack them on our rack. We log that as adding 20 real wheels to our total. Then an order for 5 wheels comes in. So we add 5, multiplied by I to get imaginary wheels, and then add that to our current total of 20 real ones. Now our status reflects both how much cheese we have in the shop and how many have been ordered. Let's hand 5 wheels over for shipping. We do that by taking our shop status and add 5i, the 5 ordered wheels, to it, multiplied by another I to get shipped cheese. Those will turn into 5 shipped wheels because I times I is -1. So they subtract from 20 real wheels while leaving the order intact. That gives us 15 plus 5i as our new shop status. We are waiting for the truck to deliver the cheese before we clear the order. When that happens, we again take our shop status and add 5 shipped wheels minus 5 multiplied by I to get how many wheels we need to clear from orders. Those minus 5i will take away the 5i representing orders we have logged to give us our new status of just 15. We have 15 wheels in our shop and no outstanding orders. But what if the delivery didn't go through? Let's rewind back to what our total was just before that happened, when the cheese was still on the way. It read 15 plus 5i. The cheese is on its way back to us. Once it's here, we check if it's still packed and good for resale. And when we've made sure of that, we take our shop status and add minus 5i, the wheels that are supposed to be cleared from orders, multiplied by another I, and this will give us real wheels we'll be putting back on our rack. Now we have 20 wheels physically and an undelivered order. So we call the customer to ask if they want us to ship it again. Unfortunately for us, they say no, and now we have to clear the order. This time we go backwards. We take our shop status and add 5 real wheels of cheese divided by I to traverse backwards through our sales cycle. This will create -5i wheels and clear the order for us without affecting the real wheels on our rack. We're now right back where we started. Not the best first day of business. But hey, at least we've got this nice setup to keep track of everything that goes on that's nice and reversible. This system also allows us to use negative numbers in regular ways, such as subtracting away cheese we got rid of because it went bad, or clearing orders customers gave up on before we even shipped them. It's pretty consistent, and operations do what you'd naturally expect. I don't think you're going to be running to your accountant demanding they switch to doing things this way, but my goal was to show you that you can indeed keep track of countable things with imaginary and complex numbers in a way that is meaningful. Who knows, maybe something like this becomes normal if we teach the next generation to understand these numbers in a way comparable to how we understand negatives today. After all, negatives were a headache for the brightest mathematicians only a few centuries ago. This brings us full circle, pun intended. We've seen how imaginary numbers arise from principles similar to those that gave us fractions and negative numbers, and that the word imaginary isn't so crazy if you think about their nature as relative to the reals. They just extend the idea of units a bit further than we're used to, and whatever you can define a unit for, you can count, whether it's a whole thing, a fraction of a thing, or something relative to a thing. I haven't really told you much about the algebraic properties of these numbers, which you'd need if you want to use them confidently. My guess is that this is something you've learned a bit about already, or if you haven't, you won't have trouble finding resources to do that. I've left some links to help you out in the description. My goal was to inspire you to recognize them in the world around you. Turns, cycles, degrees of freedom, these are concepts that reach much further than just geometry. Nature isn't shy to show them in many different forms. Feel free to engage me in the comments. If you're not watching this in some faraway future, I'm just getting started and there's a good chance I'll find time to answer. I've also prepared other videos to publish in the near future, so consider subscribing if you want them to pop up for you when I put them out. Thank you so much for watching. I hope you enjoyed and learned something new. Have a wonderful day. Bye!